In this video, we will talk about inverse trigonometric functions. The material corresponds to what's covered in section 7.1 of the textbook. Earlier in the course, we learned about inverse functions. Let's say we have a function f of x, and it has an inverse function. Well, the way that we usually write the inverse function is we write the function with the f, and then we write what looks like an exponent minus 1 of x. It's not really raised to the minus 1 power. This is just supposed to mean inverse of the function. One of the things that's true about an inverse function is that when we take the inverse function of the original function of x, the result is x. That is, we get x back. The same is true when we find f of the inverse function of x. We also know that the domain of the inverse function is the range of the original function, and the range of the inverse function is the domain of the original function. So that when we graph the inverse function, each point on the original graph, x, y, corresponds to a point on the inverse function graphed with y, x. The resulting graph of the inverse function is a reflection of the graph of the original function about the line y equals x. Now let's look at a specific function. Y is equal to f of x, which is equal to x squared, where the domain is that x can be any real number. That is, the domain of x is the set of real numbers. This function is not a one-to-one function. Namely, it isn't the case that for every y value, there is a unique x value. We can see this by drawing a horizontal line across the graph shown here in blue. If this function were one-to-one, we should be able to lay down a horizontal line anywhere on the graph and cross the graph at most once. The horizontal line here, however, crosses the graph twice, so this function fails the horizontal line test. It is not a one-to-one function, and it is therefore not invertible. Now let's look at g of x, which is identical to f of x, except that its domain is restricted to non-negative values of x. That is, x is greater than or equal to 0. G of x passes the horizontal line test. So it is a one-to-one function, and it is invertible. So what we see from this example is that some non-invertible functions can become invertible if their domains are restricted. Now let's consider the function y is equal to the sine of x. From the graph we can see that it fails the horizontal line test, and therefore it is not invertible. However, if we consider 1/2 of a period of this function, here marked in blue, namely the part of sine of x where x is between minus pi over 2 and pi over 2, we can see that this new function is invertible. Let's look at this domain-limited function a little more closely. It includes minus pi over 2 and pi over 2, and the range is minus 1 to 1. This is the portion of the sine function for which we can find the inverse. In fact, it's the longest portion of the sine function for which we can find the inverse. It's true that we could have selected a different portion of the same size, certain portions of the same size, but by convention, we choose the interval between minus pi over 2 and pi over 2. If we restrict the domain this way, we can find the inverse sine function. Let's begin with y is equal to the sine of x. To find the inverse function, we swap the x and y values, obtaining the equation x is equal to the sine of y. This is the inverse function defined implicitly. However, we'd like to define it explicitly, which means we want to isolate y on one side of the equation. To do that, we take the next step of taking the inverse sine of each side. Because of the way an inverse function is defined, we know that the right side of the equation simplifies to y. And we know also that the domain of the inverse function is that x has to be between minus 1 and 1, and that y needs to be between minus pi over 2 and pi over 2. The inverse sine function is sometimes called the arcsine. You might see that notation in certain math books, but we'll stick to calling it the inverse sine function. So here's the graph of the domain-limited sine of x function that we looked at before. And here's its domain, and here's its range. We can graph the inverse sine function by mapping every x comma y point of the sine of x graph to a y comma x point. When we do that, we can see that the domain of the sine of x is the range of the inverse sine of x. And we see that the range of the sine of x is the domain of the inverse sine of x. The two graphs are mirror images of each other reflected about the line y is equal to x. Now let's look at some specific examples. First, we're going to consider the equation that the inverse sine of 1 is equal to theta. We'd like to know what theta is. We know that theta has to be an angle between minus pi over 2 and pi over 2 radians. Keeping that in mind, we rewrite the inverse function as sine of theta equals 1. And then we can check over our inventory of theta, comma, sine theta pairs that we know, ones for common values of theta. We see that the angle for which the sine is 1 is pi over 2. So that means that theta equals pi over 2. And we can see this point on the graph of the sine function. In fact, it falls within the limited version of the sine function between minus pi over 2 and pi over 2. As was true for other pairs of functions and inverse functions, when we take the inverse function of a sine function, the result is the argument. But in this case, that's provided the argument falls between minus pi over 2 and pi over 2. And when we take the sine of the inverse sine, we will recover the argument, provided that that argument is between minus 1 and 1. This is straightforward in some cases, such as when we take the inverse sine of the sine of pi over 2. Since pi over 2 is within the interval minus pi over 2 to pi over 2, the inverse sine of the sine is the argument, namely pi over 2. But what happens when the argument is outside the interval? Let's take a look at the unit circle. The angle 5 pi over 8 is marked in pink. We see that the sine of this angle is y. That's also the sine of 3 pi over 8, an angle marked here in blue that is within the permitted interval. So we will use the sine of 3 pi over 8. We substitute it into the expression, and the result is 3 pi over 8. Generally speaking, when we have a problem like this, where the original angle lies outside the interval, the preferred interval, the specified interval, we need to find an angle in the first or fourth quadrant that has the same sign as the original angle, and use that to solve the problem. Now let's consider the function cosine of x. We can see from the graph that it fails the horizontal line test, so it's not a one-to-one function and it's not invertible. It's very similar to the sine function. However, when we limit the domain to 0 to pi, the resulting function is invertible. This portion of the cosine function is half a period. We could have chosen any half period, but by convention we choose the domain to be between 0 and pi. We can see that the corresponding range is minus 1 to 1. We can graph the inverse cosine function using the same techniques as for other inverse functions. And again, the range is the same as the domain of the cosine function, and the domain is the same as the range of the cosine function. The graph of the inverse cosine function is a reflection of the graph of the cosine function about the line y is equal to x. Now let's consider the case where we want to know the value of the inverse cosine of minus the square root of 2 over 2. This value is about minus 0.7, which is between minus 1 and 1, so we will be able to find its inverse cosine. We rewrite the function as the cosine of theta is equal to minus the square root of 2 over 2. And then we look at our table of cosine values for selected angles. And we see that the angle that it matches is 3 pi over 4. And here's the point on the graph of the cosine function. In general, the inverse cosine of cosine of x will equal x as long as x falls within the interval 0 to pi. And the cosine of the inverse cosine of x will equal x as long as x is between -1 and 1. Now let's look at some more examples. Here we have an angle pi over 12, and we want to know what the inverse cosine of the cosine of this angle is. Since pi over 12 is within the interval 0 to pi, the answer is pi over 12. That one was straightforward, but what happens when we change the angle to -2 pi over 3? This angle is not within the interval 0 to pi. However, we can use the fact that cosine is an even function to help us. This means that the cosine of a negative angle is equal to the cosine of its positive counterpart. So the cosine of -2 pi over 3 equals that of 2 pi over 3, and 2 pi over 3 is within the interval 0 to pi. We substitute, and the answer we obtain is 2 pi over 3. Here's another one. Let's say we have the cosine of the inverse cosine of pi. In order for us to find the inverse cosine of a value, the value needs to be between -1 and 1. But that's not the case here. Pi is greater than 1. It's 3.14 and so on. That means the inverse cosine is undefined. And if it's undefined, when we try to take the cosine of something that's undefined, that result is also undefined. Now we're going to look at the tangent function and consider its inverse function. As was the case for the sine and cosine functions, the tangent function is not invertible. But a single period, and by convention, the one that we use is between -pi over 2 and pi over 2, is invertible. We'll notice that the interval, though, does not include -pi over 2 and pi over 2. Those are asymptotes of the function. To obtain the inverse tangent function, we begin with y is equal to tangent of x, graphed here in green. We swap the x and y values, obtaining an implicitly defined inverse function. The inverse tangent is graphed in blue. Its domain is the same as the range of the tangent of x, namely the set of real numbers, and its range is between -pi over 2 and pi over 2. So when we consider the composite function inverse tangent of the tangent of x, the result is x as long as x is between -pi over 2 and pi over 2. And there's an error in this slide. That should be -pi over 2 less than x less than pi over 2. I apologize for that. And in the composite function, tangent of inverse tangent of x, the result is x, and x can be any real number. So let's say we have the inverse tangent of 1. What does this equal? 1 is within the interval -pi over 2 to pi over 2. So let's rewrite the function as tangent of theta is equal to 1. And in the chart of common angles and their tangents, we see that the corresponding angle is pi over 4. We can use inverse trig functions in more complicated expressions, like this function. Here, we'll start by finding the range of the function f of x. Because f of x contains the trig function sine of x, x is restricted to being between -pi over 2 and pi over 2. So let's begin with y equals 2 times sine of x minus 1. Now sine of x is equal to y plus 1 all over 2. And we know that the sine of x has to be between -1 and 1. So we set up the inequality, substituting the expression for sine of x. And then we multiply all three terms of the inequality by 2. And then we subtract 1 from each part of the inequality. And that gives us the range of the function. The range of f of x is between -3 and 1. Now, starting with f of x, again, this same function, let's find the inverse function. Again, the value of x is restricted because of the sine x function within the expression. An implicit form of the inverse function is obtained by swapping the x and y values. We add 1 to both sides, we divide both sides by 2, and then we take the inverse sign of both sides of the equation. We know that the domain of the original function f of x is between minus pi over 2 and pi over 2, and its range is minus 3 to 1. This means that the domain of the inverse function is minus 3 to 1, and the range is minus pi over 2 to pi over 2. Now let's look at the equation 3 times the inverse sine of x is equal to pi. When we simplify, we obtain the expression sine of pi over 3 is equal to x. Now pi over 3 is within the interval minus pi over 2 to pi over 2, so we will be able to find the sine of pi over 3. Looking at the table of common angles and their sines, we see that the sine of pi over 3 is the square root of 3 over 2. So this means that x is equal to the square root of 3 over 2.